My name is Henrik Plötz. I'm a computer scientist living in Berlin, and this is Blockchain 102. I have been doing things with cryptography for about 15 years now. I'm not a cryptographer per se, but mostly interested in communications protocols. I've been doing a lot of access control RFID related research. As of late, I have my own company. We're doing payment stuff. Fair warning, I did have some Bitcoin in the early 2010s. I sold the last of it around 2016, I think. And since then, I've been more and more concerned with basically the blockchain hype and how it captures resources. And resources does not only refer to electrical power, but also engineering capacity, public attention, and mind space, basically. This talk is not going to be Bitcoin 101. I assume a basic knowledge of the Bitcoin and Ethereum networks, at least what they are and how they are used. I'm not going to introduce the basic concept of blockchains. What I will do is spotlight several interesting projects and protocols in relation to that. I am going to play fast and loose with the definitions. I'm not going to stick to a very specific definition of what a blockchain is versus a hash chain. Anything basically related or in the vicinity of distributed ledger technologies is fair game. I hope by the end of this talk you will have noticed that I'm not a big fan of anything I'm about to show you, and I do reserve the right to poke fun at any and all bad ideas. As a baseline, I think Bitcoin is a work of genius. It is very elegant in its simplicity. The original paper by Satoshi Nakamoto in 2008, showing the first combination proof of work distributed ledger and hash chain, solved the Byzantine agreement problem on in a permissionless environment that is Sybil proof and only based on reasonable cryptographic assumptions. Like I said, it is elegant in its simplicity. It solves the problem for a very specific niche, and there are at least 3 or 4 design decisions that are very integral and irreducible in the Bitcoin system. Taking any of them out will harm or break the entire system in obvious and or non-obvious ways, which of course is why people are going to do that. Bitcoin itself has only very limited scripting in its transaction scheme. It's not designed to be a programming language. It's not designed for smart contracts, but the scripts are merely a very nice serialization format for authorization decisions, so that you don't have to hard code into the network all the possible authorization schemes that should be able to exist, but any user of the network can build a script that authorizes the spending of funds in any way they like. Bitcoin is a very elegant scheme, and it's mostly useless. That's the point. That's what I'm sticking with, since the only purpose it can have is a global, decentralized, globally available currency, but it does have very, very low transaction throughput and very high energy usage at that. Ethereum came later. It tried to improve by having a full-blown Turing-complete smart contract language. Basically, Ethereum is a global computer that, as a side effect, also processes payment transactions. First, we're going to look at Bitcoin, Ethereum, both proof of work. We're going to look at the different proof of something schemes. The easiest one, of course, is proof of authority. Works mostly like you would imagine it's going to work. You have the normal transactions, you have nodes that verify that transactions are correct. They put them into a block and sign the entire block with their own private key. And a sufficient quorum of authoritative nodes needs to sign a transaction block for it to become valid. Very simple, very efficient, and requires trust in those authorities. How they are chosen is completely out of scope and non-obvious. It is one of the standard constructions for private or permission blockchains. So that's why we say those are basically just glorified databases. A slight step up is proof of stake. Proof of stake, though, is basically the same as proof of authority, except that authority is now indirectly established by some sort of stake, such as token holdings. If you hold enough token of the underlying currency, you have more stake and therefore more authority. These systems may sometimes offer an integrated punishment mechanism called slashing, so that if you wield your authority in an inappropriate way, if you lie, you're penalized. Currently, proof of stake is the holy grail for the established proof of work systems to get rid of this energy waste stigma. For example, both Ethereum and IOTA, I'm going to talk about IOTA later on, currently are planning to pivot to a proof of stake based system any day now. Proof of stake has a very hard problem. How do you initially distribute the stake? That's why I said it's essentially the same as with authority. You need to somehow select the authorities you trust. You need to select stakeholders you trust. And they then get to determine what happens on the network. A very popular mechanism to do that is sale of tokens, which is why I have this little red flag next to it. Sale of tokens or initial coin offering. I'm going to invent a network, the very cool Cool Chain. I'm going to sell $600 billion worth of Cool Chain tokens. And then you all are on my network, and I'm $600 million richer. I don't care what happens to the network afterwards. An alternative to this is to bootstrap the proof-of-stake system off of an existing blockchain. For example, the Ethereum chain, or IOTA is going to do that, I think, today. Which is, yeah, it doesn't have the same problem. No. It doesn't have the same benefit for the creators of the network. Still, the general problem with proof of stake is that there is no built-in defense against centralization. Bitcoin solves the centralization problem by sheer physics. It's very, very hard to have more than 51% of the global computing power currently. But in a proof-of-stake system, there is no built-in defense against anyone accumulating 51% of stake on their account or on any sock puppet accounts. This is what I mean when I say there's no Sybil resistance, because on the internet nobody knows if you're a dog, and nobody knows who and how many you are or claim to be. Deeply ingrained problem is that even if you bootstrap the thing correctly, you have no defense against it becoming centralized later on by a stake being transferred and accumulated onto one big stakeholder. The other POS is proof of storage. I'm not going to talk about that very much. There's one scheme that has gained notoriety because basically the introduction of the Chia network crashed the global SSD market. This was very, very hard to buy any disks at that time. Also, the operations on this network destroy SSDs in less than a year, so it's really expensive to operate, even though it doesn't use electricity. It uses SSDs. And basically there's no other use. So I'm not going to talk about it later. The funniest proof system, and actually the thing I came across that motivated me to give this talk, is proof of elapsed time, also called POET. The idea is very simple and ingenious. Instead of computing hashes for proof of work, and proof of work in this case means waiting some time, instead of computing hashes, you just do nothing, you go to sleep. Compared to a proof of work system, this offers incredible energy savings. And it's a drop-in solution. It behaves exactly like a proof of work system in any network. You can just swap out the proof of work system for a proof of elapsed time system. Mostly it makes sense in permissioned environments, private blockchains. I do have a small, there is a very small question, a teeny tiny issue. Which guarantees do other nodes have that no one cheats, no one is going to wake up earlier than assigned? Well, of course, Intel SGX. It's the, for those who don't know that, SGX is the secure enclave in Intel processors. Intel guarantees that inside this processor, secure computation can take place. And programs that run inside the enclave can prove that they are running in an official Intel secure enclave and are not being controlled by anybody else from the outside, and thus allow trusted execution. Small problem? Obviously, this wasn't going to be secure forever. There was a very nice break of Intel SGX 2 years ago. It went so far that they offer an attestation as a service. There's a Twitter account, and if you need anything signed by a real Intel SGX enclave, anything at all, any attestation to any fact, you can just tweet it to this Twitter account, and they will happily sign it for you. And this is one of the underlying topics I want to draw your attention to, is that some of these systems appear to be secure, but they're just shifting the security barrier somewhere else, and hope you don't look and hope you don't look too closely at how and where the security is now. For example, MobileCoin is the other extreme, basically. MobileCoin has a proof, I would call it proof of complexity. MobileCoin is a mobile device-focused new cryptocurrency started last year, and it pulls every cryptographic register there is. They're using Stellar Consensus Network, they have zero-knowledge proofs for everything, risk-trader abstraction, Schnorr anonymous signatures, Peterson commitments, you name it, they have it. There's a very good book about it, this Mechanics of MobileCoin I've linked here. So even though I'm showing this part of the abstract to scare you, I'm very grateful that it exists, because not everyone has an abstract that so clearly states what they are doing and what they are hoping to achieve. Many of the documentation, a lot of the documentation that I've been reading for this talk doesn't clearly tell you what they are doing and why. Two small problems with MobileCoin. The entire token supply is pre-mined, which is one of the other red flags. 85% of the current MobileCoin in existence, and all the mobile coins that will ever be in existence, are held by the creators of MobileCoin. They can sell it to you at will. and their security against double spending. So they have security, they have privacy guarantees that probably maybe are good. It's, like I said, it's very complex, and I wouldn't bet on there not being any implementation errors. But absent any implementation mistakes, their privacy guarantees and properties are probably good. But their security against double spending is entirely reliant on SGX enclaves. See previous slide. Circling back to Bitcoin and misusing Bitcoin, I introduced it as not having an entire full-blown scripting language, but you can still do cool stuff with it nevertheless. One of the earliest examples of that I saw was due to Dan Kaminsky, who sadly passed away this year. In 2011, in his Black Ops of TCP/IP talk, he presented a tribute to Len Sessaman, who died that year, on the Bitcoin mainnet that is embedded in the Bitcoin blockchain. And thus, verifications of the entire blockchain is dependent on this tribute being present, which is a very nice idea. And I'm not sure, but I think it was one of the first examples of this. A lot of people have embedded stuff into the blockchain later on. And a very moving memorial to a friend. Another very cool hack that is actually not being used as a hack anymore, but is in production, is the Lightning Network. Starting in 2016. I'm going to explain this in a little bit more detail, but not entirely in detail, since we have other content to get to. What's interesting about the Lightning Network is that it works with Bitcoin more or less without changes. There were very small changes made to the Bitcoin mainnet, but no fundamental changes. There's no new scripting language, only new instructions in the existing language. It's a clever use of time locks and multi-signatures. One of the features that most people aren't aware of is that not only can the Bitcoin scripting language allow you to put signature restrictions like possession of a private key on spending of Bitcoins, but you can also put a time lock on it and can say that a specific amount of Bitcoin can only be spent after some time. Basically, time either in Unix seconds or in block height. Since the Bitcoin network as a whole has a more or less predictable block time of 10 minutes, you can rather reliably say that some amount of money cannot be spent for 48 hours, for example. And that's the basic idea here. Two parties collaborate to open a so-called Lightning channel or payment channel. They need to fund this channel on the main chain. Like I'm putting the main chain here and the Lightning channel or the entire Lightning network at this point. So a properly functioning Lightning channel only is visible in two transactions in the main network. There's the funding transaction, the one up here, that basically locks up some money in escrow, essentially, in escrow for the channel. And after that, the two parties exchange transactions amongst themselves. The main network does not need to know about these transactions. And they can send money back and forth. In this example, both start with, for example, 2 Bitcoins. Both commit 2 Bitcoins for this channel, so the channel has an entire capacity of 4 Bitcoins. Each party starts off with 2 Bitcoins at first, and then they can transfer or exchange transactions that transfer any arbitrary partial amount of that in either direction. So I'm starting with 0.2 Bitcoins to B. Now the internal state is that B has a bit more money. Then I'm transferring, in this example, 1.5 in the other direction. Now B has less money, and so on and so on and so on. These transactions are very fast, since they are just two signatures and a TCP connection, and therefore can happen instantaneously. At the end of the channel, both parties can mutually agree to close the channel, and only the last state is written back onto the main blockchain. The cool thing about this is that due to the clever use of time locks and multisigs, all the amount of money in the channel is protected against a cheating party. These intermediate blocks need to be signed by both parties. So the end transaction is signed by both parties. But there is a Damocles sword, basically, hanging over this using the time locks. If any party cheats, the other party automatically gains the authority to claim the entire funds for themselves. This prevents the parties from cheating, because who wants to lose 2 bitcoins? But also means that the maximum outstanding amount of money on this channel is limited to the escrow amount. This, in the channel, for example, in this example, at no point can any party owe the other more than 4 bitcoins. If you want to buy something really expensive, 4 bitcoins is a bit much, but if you want to buy something really expensive, you cannot use this channel, you need to close it and open another one. And that's the other big problem. The money that is held in escrow for this channel cannot be used for anything else. If you open a Lightning channel to someone, that money is gone for the moment. And even worse, through the time lock mechanism, if the other party misbehaves, you cannot access the money for some time, 48 hours, for example. So it is a very cool hack, but I don't think it has any particular usefulness, especially since due to this because the outstanding amount cannot the outstanding money amount cannot exceed the entire capacity of the channel, it does not lend itself to being used, for example, for payments. It's okay if you have a friend and you lend them like a bit of money today and they pay you back tomorrow. Day after that, you don't have any money with you and they lend you something and you pay them back. But for a channel to exist over a long time, its mean amount needs to be 0. It must be the same on both sides. While most transactions in most systems are in a merchant and customer relationship. If I buy something, I pay money to the merchant, and very seldomly do they pay me money. This is the fundamental problem of the Lightning Network. They do have an extension. I've been drawing this with 2 participants. Lightning channels can be chained. So if A and B have a channel and B and C have a channel, there can be a value transaction between A and C, mediated through B. But the problem that the outstanding amount on the channel cannot exceed the funding amount doesn't go away. Back to something that was actually designed to be programmable, Ethereum. Very shortly after the introduction of Ethereum, there was the DAO. At that point, that was a singular noun, the Decentralized Autonomous Organization. Today, DAO is mostly used as a collective noun, basically a DAO, but at that point it was the DAO. It was a cool idea. It's from the Code is Law people. Basically, you have a venture capital fund that anybody can contribute money to, Ether to. And anyone who has contributed money into the fund has voting rights and basically governance rights on the amount and can vote on where this money should be invested, proportional to the amount of money they invested. It had its own token at that point, and was crowdfunded end of June 2016 and sold at that time for more than $150 million. This didn't last long. There was a vulnerability in so the DAO has a function to split out sub-DAOs if there's no consensus about what's supposed to happen. So if the majority of the funders decide to do something that a minority disagrees with, the minority can split out their money into a child DAO that then behaves like a normal DAO. And anyone can propose to create such a child DAO. The code that processed that request had a bug. Classic time of check, time of use bug. The smart contract first retrieved the Ether to be sent to the child DAO from the main DAO, and only then checked the balance of the account that proposed the split. But at that point, a recursive call is possible, so you can nest this problem. Which means the transaction, the nested transaction happens so it deducts money from the main, funds it into the child DAO, recursive call, deduct money from main, fund into child, deduct money from main, and so on. And the check against the balance would only happen afterwards. Someone found this, and, well, people say used it. And by June 2016, like 2 weeks later, about $50 million worth of tokens were in the child DAO that was supposed to be controlled, about to be controlled by one party. Luckily, as luck would have it, there was a built-in waiting period for proposals to go through and people to read their mails and stuff like that. That meant all the money that was in this child DAO couldn't be transferred out for at least 48 days, for exactly 48 days. So there was some discussion time as to what should happen now. This was the big discussion of that time, because one party says code is law. Someone used the code, and obviously it's correct what they did because the code allowed that. Though the main Ethereum network did not quite see it that way, which led to a hard fork of the entire blockchain. That's why we have Ethereum and Ethereum Classic now, and I don't think anyone uses Ethereum Classic. Like I said, the DAO had its own token, was one of the first. There is now a generic mechanism to create your own tokens. It's basically an API specification. If your contract fulfills this API, then you are an ERC20 token. And these tokens behave like money. Something you can transfer. You can query the balance. Those are the only relevant functions. So if you put a contract onto the Ethereum blockchain that fulfills this specification, you have your own money. Lots of people do that. There's more than 480,000 token contracts currently on the blockchain, on the Ethereum blockchain. And all the details of those tokens are up to the token creator. Obviously, it's a smart contract. It only has an interface, and you can deposit and transfer money. Where this money comes from, this amount value comes from is not specified and entirely up to the token creator. These tokens can have their own value independent of the Ether, and some do. And that's how that works. What you can use this for is what I call crypto-enabled financial trickery. Since these tokens can basically only be traded, you have Dogecoin, and if I would want Dogecoin, I could buy it from you, and then you would have some other amount of currency, some other kind of currency. And now we have over 480,000 different kinds of currency to choose from. This enables exciting opportunities of arbitrage. If I find two marketplaces that sell token pairs at different prices, I can buy one token at the cheaper price and sell it at the more expensive price. That's the classic thing that you would also do on a normal stock exchange. The cool thing about Ethereum and smart contracts is that the smart contracts are executed automatically and enforce automatically the contract stipulations, no matter what they look like. One of the really mind-blowing or very mind-opening things that you can do with that is an uncollateralized flash loan. Basically, it's a smart contract that always has the following form. I give you some amount of money, you do whatever you want, and then you return the money with some fee, plus some fee. You're completely free to do whatever you want in this step. You can, like I said, exploit arbitrage opportunities. You can sell something at a different marketplace and then buy back. The important thing is that you pay me back plus interest. And the cool thing about the Ethereum or the smart contract language is that this is guaranteed to happen atomically. Either the entire thing happens or nothing happens at all, except for some gas spending. If you cannot return the amount, for example, because your cool arbitrage trick didn't work out, it's reverted and never happened. So I can enforce for you to pay me some money, and you can. So that's for me, good for me. Good for me is I can enforce you to pay me some interest, and good for you, you have a lot of money. Like I said, it's very good for exploiting arbitrage opportunities, and it's also very good for exploiting smart contract vulnerabilities, because a lot of these need some funding, and if you have a vulnerability that doubles your input, for example, it's very cool if you can borrow $100 million for like $10,000 in interest and then double it. And finally, decentralized finance, DeFi. DeFi? Decentralized finance, DeFi. It's just the umbrella and marketing term for everything we just talked about. It allows most operations that you can do with traditional financial instruments, but on the blockchain. Borrowing, lending, flash borrowing, high-frequency trading, price speculation, and swapping between token pairs. Like swapping Dogecoin for... what's one of the other coins? Dogecoin for Tether or BEG, something like that. Now, this is one of the subjects I'm most often laughing about, because as you can see on this slide, there's a huge amount of money in here. There's a hell lot of money bound in DeFi contracts, but the complexity means that very often, well, code is law, but the law does not always say what you thought it is. By my estimation, and when I searched for that, I found this website, which very graciously already has an entire list. I didn't need to compile it. By my estimation, about approximately every other week, someone exploits a bug in one of the DeFi systems to the tune of 10 to 100 million US dollars. These are just from like the last 2 months. Now for something completely different, the IOTA network. IOTA is not a blockchain. So like I said, I don't want to dwell on the terms, but they call themselves a tangle. It's a directed acyclic graph. It's not a chain, but every transaction is supposed to confirm to other transactions. It doesn't have any proof of work, so it's very fast and energy efficient. It doesn't use a lot of energy. I'm not sure if it's efficient, if it doesn't do anything, but it doesn't use a lot of energy. It doesn't have any proof of work. It doesn't have any proof of anything, really. It doesn't have any transaction fees. You just are required to verify two other transactions. It's designed or marketed for Internet of Things networks. It's actually run by a foundation located here in Berlin. And the thing that sets it apart from one of the things that sets it apart from all of the other established players is that it's not a decentralized system. Their consensus protocol is that they have a central coordinator that has to sign off on every transaction. If the coordinator didn't verify it, it didn't happen. There were several attacks on the IOTA system in the past, and the foundation luckily could stop the attacks by basically just stopping the coordinator. Like I said, the coordinator is just one of the things that makes this one unique. The other unique thing about IOTA is that they want to be unique. They have their own, or they had their own home-built cryptography. One of the rules is never roll your own cryptography. And not only did they build their own cryptography, they did it in trinary. So in their system, there isn't just 0 or 1, but they have -1, 0, or 1. Everything is a twit. And of course, their custom-built trinary hash function was broken. In 2019, the IOTA Foundation did not react favorably to this. The second link on this page has some of the history, or some of the meta history, basically. There was very interesting Twitter discussions and threats against the researchers, threats of legal action, including the IOTA Foundation claiming that, or the creators, I'm not sure of the foundation itself, the creators claiming that they knew about the vulnerability and it was there on purpose to act as a sort of copy protection. Their defense is that if anybody would copy the IOTA protocol, since everything is open source, and build a clone IOTA network, they could then use this vulnerability to shut down the other network, which is a bit of bullshit. In the aftermath, they removed the broken hash function and replaced it with one that's based on Kekak, the SHA-3 hash function, but still in trinary, and it's still broken. Nobody cares. It's still broken. Nobody cares. Okay, let's move on in our alphabet soup. SSI. It's not server-side include this time. SSI is supposed to stand for Self-Sovereign Identities, and Wikipedia defines this as an approach to digital identity that gives individuals control of their digital identities. And no one knows what that means. There's no single standard, nor specification, or shared understanding of what this might be. The graphic I put here is one that's most often used to explain how this is supposed to work. It's indistinguishable from a standard PKI attribute certificate issuance. Like you have an issuer that issues a certificate that's stored in a wallet and can then be presented to a verifier. For some reason that nobody has been able to explain to me to my satisfaction, it's also stored in the blockchain. What this diagram lacks, and what most of these systems tend to lack, is a very crucial additional arrow. It's very good if I have the cryptographic proof that some credential was really issued by a certain issuer, but I still need to get trust in that issuer from somewhere. I still need to know that they are who they claim they are. And this is something that's basically entirely ignored in all of the self-sovereign identity schemes I've seen and coming up on. Key terms. There's this thing called a Decentralized Identifier, DID, which is supposed to be the abstraction. There's a W3C standard on that, and the registry currently lists 114 mutually incompatible DID methods. Like I said, it behaves like an attribute certificates. This is called a verifiable credential. And one of the only new things, or one of the things that established protocols don't have, it's not new, is that they should support selective disclosure. Selective disclosure means if I get a credential to multiple facts, like my name is Henrik, my last name is Plötz, I'm living in Berlin, I can then present this credential but block out some of the fields and just prove, for example, that I'm living in Berlin. If I want something from the Berlin authorities, they might not need to know who I am, just that I can prove that I live in Berlin. It's one of the key features, for example, of the uProof system due to Stefan Brands in 2000, I think, which was built into Microsoft CardSpace, I think, and for some reason completely vanished off the face of the earth. Nobody ever heard of it again, but it did solve all of this in 2000 already. Nevertheless, all these self-sovereign identity people are very eager to show you their use cases and their showcases. For example, this one presenting information to an employer. In the future, you will have your diploma or your master's degree as a verifiable credential that you can then attach to your CV when applying for a new job, and your employer will be able to verify that and doesn't need to trust that you didn't change your grades. Like I said, very small, insignificant issue. The employer still somehow needs to trust the issuer. I can go on the blockchain and open the very cool University of Coolness and issue master's degrees in coolnessness and give everyone A grades. And I can prove that I really am the cool University of Coolness. But somehow the verifier, the potential employer, still needs to know whether I am an officially accredited university whose master's degree is worth anything. And at that point, you have a very standard PKI structure. You have a central authority, like a list of good universities. And from there on, you can delegate the trust down. And you don't need any of the decentralized stuff. And in either case, you don't need any of the blockchain stuff. I've never understood why. No, that's not all right. I made this point on Twitter once, and someone actually emailed me. I'm not sure, either ID Union or Lissy. Someone emailed me and said that they kind of know that they don't need it, but the problem they are solving is that there are so many interested parties in the space, so many companies who want to promote their own wallet product, that there's no way that they can decide on a governance structure, on a PKI structure, on who trusts whom and who delegates trust where. So instead, they are putting it all onto the blockchain and thereby completely erasing the trace of where the trust chain comes from, and hope their respective companies don't notice. So basically, it's money laundering for PKI is what they're using the blockchain for. A related standard in this space is DID.com. It's from the Identity Foundation. Very cool domain name, if I might say so. Yeah. It's a long standards document. It's a really long standards document. It has everything. It has JSON web messages, JSON web token. It has a custom asynchronous request-reply messaging scheme with multiple parallel asynchronous threads of communication. It has a routing layer, transport layer, discovery. There's everything in there except provisions for recipient verification. So I can have my decentralized identifier, my verifiable credential. I could present my verifiable credential to someone selectively so that they only get to know what I want them to know, except I have no idea who they are. Which brings us to this year's news, the ID wallet. Exactly in the last week before this year's German parliamentary elections, our esteemed government released an app, or one of the intermediaries, released an app to a big PR fanfare called ID Wallet, or released the use cases for that, which was supposed to be a self-sovereign identity system based on DID.com that could in the future be used for a lot of other things. We're completely ignoring at this point that Germany already has an eID system that works, but it's not cool, it's not blockchain, it's not hip. So this ID Wallet app, you can use it to create a self-sovereign identity called Basis ID. And this self-sovereign identity is created by having the Bundesdruckerei sign a dataset that they extracted from your national ID card. So the self-sovereign identity is created by the Bundesdruckerei, essentially. And you can then use this identity to query the Federal Motor Transport Authority for a copy of your driver's license. That then is assigned to this verifiable credential. Nothing you couldn't just do with a database, a signature, but it is a blockchain system. And it didn't end well. A few days after public release, the entire thing was stopped. The official reason given is that there was too much interest, too much load due to unanticipated high interest in the system. What you will find on Twitter, if you looking into Lilith Wittmann and Flipke, who were the main actors in the space, is that the entire thing was run on very badly maintained infrastructure. There were DNS zone transfers, there were open subdomains, a lot of things not good. And the coup de grace is that Lilith showed the privacy problem mentioned earlier, that even though I can present present my verifiable credential to someone in a secure way, I have no idea whom I'm presenting it to. And that's inherent in the protocol. There's no way to fix it and no plans to fix it. So the thing remains shut down for the time being and probably for good. Hopefully. On the subject of silliness, NFT. NFT stands for Non-Fungible Token. So for comparison, the tokens I talked about before, the ERC20 tokens, are fungible. Every token is the same. You can replace every token with any other. In Bitcoin, even there is no stable token. Every time you spend Bitcoin, your existing Bitcoin gets destroyed and a new Bitcoin is created. ERC20 tokens don't really need to exist in any exact meaning of the phrase. But still, it's just the value. There is no countable token, and not only no countable, there's no unique token. The other standard, the newer one, ERC 721, specifies the API for non-fungible tokens. What it essentially does is track every token individually. The token gets a token identifier. And the blockchain records who's the identifier of the current owner of the token. And what the smart contract then allows is transferring the token from owner to owner. Normally it doesn't store any other information other than who the current owner is. So this emulates basically a collectible. A token can be created on the blockchain and then sold and resold. But now you might be asking, where do these JPEGs come in from, of which I've heard so much? What you can do in the token standard is associate metadata with the token. Actually, you can't. You can associate an URL with the token that can point to metadata. And this metadata might then optionally point to an asset file. Could be video, could be a 3D model, anything, or some other metadata like the name of the token. There's something I'm not going to talk about that's called the interplanetary file system. It's a decentralized storage system that actually behaves mostly as you would like it to. Most crucially, if you point to an IPFS address, it's immutable. But that's not the standard, wasn't the standard for a long time. For a long time, all the metadata and the data was just stored on the server of whoever minted the token, or of the platform that the token was minted on. And Moxie made this very cool demonstration where you can look at the identical non-fungible token on different platforms, and it would display differently because the metadata points to a URL that can behave differently depending on where you come from. So what are NFTs good for? Basically scams. One of the problems is that there's no verification requirement, no relationship to any real-world identity. Anyone can mint any asset into an NFT and sell it. They don't need proof of ownership. And if you believe that, I have a very nice bridge to sell you. The different platforms where you can create and sell NFTs mostly are tired of the problem now and are very much slower to respond to complaints now. There are apparently there are people out there who just go through, for example, DeviantArt, take every image from there, make an NFT out of it and try to sell it. It's like if you go on Twitter and say, I need that on a t-shirt, there will be a bot that offers to sell you that t-shirt, even though it probably doesn't have the copyright on whatever you responded to. A very cool thing someone found on Twitter the other day is that, related to the previous slide, if a lot of these platforms actually store the data, the NFT data, just on Google Cloud services, and Google's takedown processes are still working. So you can remove the NFT content without cooperation from the NFT platforms. Another problem, it's very complex, the entire thing. This leads to many, so even if there are no engineering or security vulnerabilities in there, this leads to a lot of successful social engineering attacks, with the added benefit that any token that has been stolen now rightfully, code is law, belongs to the no owner. There was this very famous case few months ago of the Bored Apes. Very high profile case. Someone got scammed out of 3 apes, I think. Value like $2 million. They successfully petitioned the trading platforms to halt trading on these tokens, which doesn't bode well for the decentralized nature of this thing, but that's that. For me, it's funny. To the people affected, it's not. Since you have no verification that an actual person is on the other side, or who is on the other side, there's this phenomenon called rug pull. Basically, you start a new project, you announce Bored Apes were yesterday's news. We are now doing evolved apes. They are better in every way, they can be used in games. Please buy them here. Enter money here. And after you've received all the money, you just clean out the accounts and vanish. This is what happens. A couple of times now. I don't have all the examples on here. Sometimes it happens even in teams. There are a couple of posts of people actually trying to start a project and then complaining that the administrator they tasked with safekeeping of the secret keys just went and took all their money and is gone now. In conclusion, there's really not a lot of uses for any of this except for Ponzi schemes and tricking people. Especially, it's all self-referential. You can do financial instruments just fine. Everything works great. It's not the most energy conserving way to do that, but it can give good return on invest. Of course, you always need to keep in mind that if you earn money, someone else lost it. So you can do the crypto-enabled financial trickery just fine. But the core problem of any and all blockchain projects is the Oracle problem. All the cryptographic stuff, all the verification, zero knowledge proofs, what have you, only works within the system. You cannot interface into the real world in any meaningful way. Because if you if you wanted to, you would need a node that acts as a mediator between the blockchain world and the physical world. You need to trust that node to, for example, accurately report sensor data or to accurately execute some actions. And if you can trust that node to do that, you can also trust the node to do that without a blockchain. Like one of the funniest projects I've heard was for trash collection. Fairness in trash collection, there's a sensor in every trash bin, and trash collectors, like municipal waste, and every trash collector gets money for the trash they collected based on the sensor readings. But the sensor nodes, of course, can't be part of any blockchain. No energy, no nothing, no connectivity. So they just report all their readings to a central server, and that central server then records all the data on the blockchain. And at that point, the central server could just disperse the amount due for trash collecting. There's no need to drag the blockchain into anything here. Put into one sentence, cryptocurrencies have, more or less by definition, only one use case, and that's Ponzi schemes and other scams. There can be, I've said that before, there can be some benefit to having pure timestamping service, so the blockchain combines timestamping and consensus. If you don't need the consensus, because anything you do is centralized by nature anyway, there can be some upside to using a Merkle tree or a timestamping chain without any of the blockchain overhead, consensus overhead. So this is the end of this talk. I will be available for your questions now.